Hello, quick video on parametric equations and the MEI C4 syllabus. I'm going to take you through a couple of questions you'd like to see, and I've basically picked out two examples from section A. First one here is where we have some parametric equation based on trig ratios and trig functions, and the second one is just a straightforward linear value. U or T, and they're going to ask us either to sketch curve, create the Cartesian equation, and find the gradient of the curve at a particular point. And in section B, they might actually ask us to find the equation of the tangent or normal or a turning point on one of these parametric equations. So I'm going to stick to section A for today and just take us through the sort of thing we're going to see there. Okay, first question. The parametric equations of a curve are x equals cos 2 theta and y equals a sine theta cos theta, and they've given us a domain here for theta. Our theta is between 0 and pi. They've then asked us to show that the Cartesian equation is that, and then to sketch the curve. Okay, so let's have a look at this and what we're going to do. In these cases with trig functions, first thing we've got to do is think about solving them using all our trig identities. So let's just list them out. So here they all are, the ones that we typically use. Got our two basics here, that tan theta equals sine theta divided by cos theta, and then cos squared theta plus sine squared theta equals 1, and the two variants on that were tans and cotans and secs and cosecs there. And then we've got a double angled formulae, cos 2 theta equals cos squared theta minus sine squared theta, and sine 2 theta equals sine theta cos theta. So there's all our variants. And what we've got to do for each of these problems is try and find an arrangement rearranging these two equations. So here I've got x equals cos 2 theta in this occasion, and y equals sine theta cos theta. And what we're going to try and do is convert those into trig ratios, and quite often we'll try and get to a single trig ratio that we can use to effectively substitute back through, or in this case we've got a classic one where from our equation here we can see that we've got a cos 2 theta, and that's driving us into double angle formulae, and using our well-known identity cos squared. In this case I'm going to write it with our 2 theta here plus sine squared with 2 theta, that's the form we're going to need to use here, is going to be equal to 1. So we can see here that we've got cos 2 theta, and therefore we need to try and rewrite the y expression in terms of a double angle and see if that helps us. And it does, because we can see sine theta cos theta we know will take us towards sine 2 theta, but we know that identity is 2 lots of that, so it's basically going to be a half. There we go. And that's helped us, hasn't it? So now we can substitute those into our equation. So our first term now is our substitution. Cos 2 theta is x, and sine 2 theta is 2y. I'm going to square those, and that's going to be equal to 1. And we can rewrite that, can't we, as x squared plus 4y squared equals 1, and that's what they asked us to show. They then asked us in the second part, so let's do the second part here. They then asked us to sketch this. Now, if you don't know what it looks like, you can plug it in your calculator, so let's do that first. In our graphing functions here, if we go up, we can set our type to parametric. Here's type parametric. Then we'll get an xt1, yt1 appear on our calculator, or it could be lower down your list, but you'll get a pair appearing. you can then type in the equations as you've been given them. So here we've got cos 2, and rather than theta it's got t in the calculator because that's immediately available. And the second line here I've got sine t times cos t, and then I'm going to press our draw function. Hey presto, it's showing us that we're looking at an ellipse. Now those of you who've memorized our looked at this curve here and memorized and remembered a series of different shapes, then x squared plus y squared starts making you look at a circle, doesn't it? And x squared, if the multipliers are not the same, we're looking at an ellipse. So effectively we've got an x squared plus 1 squared here, and a y squared divided by 1/2 all squared equals 1. That's the standard form of an ellipse, where these values on the bottom are the actually the extreme values of our ellipse. So let's just draw that. So our extreme values of x are 1 and -1, and our extreme values of y are 1/2 and -1/2. There we go. So that will be our ellipse, and it's centered at the origin here. We've not got anything inside with our x squared or y squared. There we are. We need to check that whether it's the full ellipse or not. So let's go back and look at what they gave us here at the start. They gave us a domain for theta, didn't they, between 0 and pi. So if our domain here is for theta was between 0 and pi, therefore we're using 2 theta here, aren't we? So 2 thetas between 0 and 2 pi, and therefore because we're using sine and cos here, we can see we're going to go the full curve, the full range of our ellipse is going to be included here. So tick, that's our first answer. We could use a calculator here, or through sketching, or create a table of values as well. Secondly, so our second type of question has just got a linear parameter, a u or a t or something like that. Here, note they haven't given us a domain, so I'm going to assume that u is the full real range, because they haven't told us otherwise. When I'm come to doing sketching, etc., they said find dy by dx of u, and hence find the gradient of the curve at the point 5, 6. Okay, so for the first part we need to find dy by dx, and in effect we're going to be using our chain rule here. We've got dy by dx equals dy by du times du by dx, and we've got our equations here. So x equals 1 plus u squared, so dx by du equals 2u, and y equals 2u cubed, therefore dy by du equals 6u squared. Okay, how are we going to use those now? Well, we're going to substitute those into our equation at the top of the pages we're now looking at it. Dy by dx equals dy by du, that's 6u squared, multiplied by du by dx. And if we're multiplying by that, we can effectively divide by the reciprocal, dx by du, which we know over here, so we can divide by 2u, and we end up with a differential, a first order differential, which will be our gradient of 3u. Okay, and the next thing they've asked us to do was to find the gradient of the curve at 5, 16, and they gave us the equations earlier. So we had x equals 1 plus u squared and y equals 2u cubed. There we go. So now we need to find the value of u for this point, the 0.56, so we can substitute it into the equation there for 3u. Well, on the left hand side we've got 5 equals 1 plus u squared. I'd usually do the x first, so that means 4 equals u squared, and therefore u equals plus or minus 2, doesn't it? And in this case we can see on the right hand side, might have got us there quicker, y value 16 is 2u cubed, so 8 equals u cubed, so u equals plus 2 there. we can see. So the gradient of the curve at that point is going to be dy by the dy by dx at the point P equals, I'm going to put in substitute in our value of u there, which is 2. So our gradient equals 6. Yeah. So I'd be writing probably in that form as my final line, equals 6. Gradient dy by dx at point P equals 6. There you go. So quick summary at the end here. They're going to give you a parametric equation. It's either going to be in the form of trig ratios and trig functions, or in some straightforward generalized t. Bear in mind that you'll want to know the domain, remember, if you're working on a trig function, and you'll have to assume one probably if you're just given a t or a u. If you need to sketch, well, you could create a table of values, or you could put it in your graphical calculator, but you do need to be careful to check your domain, which part of the curve that's on the screen is actually in the domain you're working with. Then you need to, second thing I'll ask you to do is to find the Cartesian equation, and we're going to use substitution there. So get it into a form where we can substitute out our t value or a trig function, maybe a sine or a cos, or that we can put it into a trig identity. In section B, they may well ask you to find the equation of a tangent or a normal. Well, we can use our dy by dx, our chain rule here, to do that, and carry out our calculations of using our parameter t or theta. And the final thing they might ask you in section B to do is to find a turning point or a stationary point and work out whether it's a max, min, or a saddle point. And in that case, of course, dy by dx equals 0. And you've got two methods of dealing with it from then on. You can either use the method of looking at seeing what's happening to your dy by dx, what the change is, if we go slightly above or below the x value that we've identified as our turning point. But you've got to watch out that, for example, is our parameter increasing or decreasing with x, because they could be going in opposite directions. Remember that we need to be looking at an increasing x, so we need to go slightly below the x, see where it is at the x value, and slightly above the x value of our turning point. Make sure you get them in the right order if we were doing one of those diagrams. Yeah. The alternate is to work out our second order differential. And if we're doing that, we need to remember that what we're doing is taking our dy by dx and using our chain rule, we're differentiating that dt, and then we're multiplying by dt by dx on the end. So you've got to remember to add follow that process and add the dt by dx part there, multiplication at the end. There you go. I hope that's of use.